of Adjunct's Professor Lecture. And I would like to thank to all participants who attended, especially our speaker, Professor Insinyur Dr. Kaharudin Dimyati from University of Malaya, Malaysia. Selamat datang di Universitas Airlangga, Profesor Kaharudin.
Terima kasih.
Hopefully, from the explanation given by Prof. Kaharudin, it can become a new knowledge and can be used, especially by FTMM students. The agenda for today's academic lecture are opening of our today's event by playing our national anthem Indonesia Raya and Hymne Airlangga. Opening remark by the Dean of FTMM Universitas Airlangga. Lecture session will be given by Professor Insinyur Dr. Kaharudin Dimyati. And closing. Before we proceed further this event, we would like to invite you to solemnly hear the Indonesian national anthem, Indonesia Raya and Hymne Airlangga.
Ada suaranya.
Aku selama ini enggak. Yang lain di mute ada nggak? Bukan juga sama sebenarnya. Ada kos nggak?
Ini coba dulu. Oh iya.
Partisipan itu dia open mic partisipan yang seperti sekedar ini soalnya nggak ada yang bantu si Rizky. Enggak, jadi itu katanya bahwa sembilan itu dilakukan operator Zoom sekali. Scroll ke bawah, cari yang open mic, lebih
Mute on.
Ladies and gentlemen, we are looking forward to listen to the speech by the Dean of FTMM Universitas Airlangga. Please welcome Professor Dr. Dwi Setiawan, M. Magister of Science in Pharmacy.
Thank you, Mas Akbar. Assalamualaikum warahmatullahi wabarakatuh. Good morning,
Waalaikumsalam warahmatullahi wabarakatuh.
Professor Kaharudin. Thank you. From Surabaya, Indonesia. Good morning, ladies and gentlemen. It is great pleasure for me to welcome you, the Adjunct Professor, Professor Kaharudin Dimyati at Universitas Airlangga, especially at Facultas of Advanced Technology and Multidicipline. I am very thankful for you, Professor Kaharudin, Deputy Dean of Faculty Engineering, University of Malaya. I also wish to thank the committees who have organized this wonderful event. I am Professor Dwi Setiawan, as Dean of Faculty Advanced Technology and Multidiscipline. Would like to say that it is our privilege and pleasure to have this great event held in our faculty. We are delighted to have you with us to participate in Adjunct Professor. I can already see big potential from this topic. I hope then through this event, we all can learn to be a good and critical thinkers. I wouldn't like to take too much of your time, so I will hand it over to our MC, Mr. Akbar, to process the next agenda. Once again, welcome and thank you very much for attending this program, Professor Kaharudin Dimyati. I wish all participants good luck. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Prof. Kaharudin.
Thank you very much, Prof.
Thank you, Professor Dwi Setiawan, for the welcoming remark. With the opening of this event, without further delay, I will hand over the next session to Mrs. Lilik Jamiatul Awalin, S.Pd, M.T, Ph.D, as discussion facilitator to guide the webinar adjunct professor lecturer to discuss about mmWave technology and device-to-device communication for beyond 5G. To Mrs. Lilik, time and place are welcome.
Okay, thank you, Mas Akbar, for the time. Welcome, Prof. Kaharudin Dimyati, to this adjunct professor lecture. Okay, welcome, ladies and gentlemen, to this adjunct professor lecture with the title of mmWave Technology and D2D Communication for Beyond 5G. Okay, without further ado, let me read short biography of Professor Kaharudin bin Dimyati. Professor Kaharudin Dimyati received his Bachelor of Engineering in Electrical from the University of Malaya in 1992. He then continued his PhD in communication system at the University of Wales, Swansea, UK in 1993 and subsequently awarded in a PhD in 1996. He is currently a professor in the Department of Electrical Engineering, University of Malaya, Kuala Lumpur, Malaysia. And so he is also now is a Dean in Faculty of Engineering, University Malaya. His research interests mainly wireless communication, optical communication, and coding theory. He has supervised to completion to date 20 PhD students and 33 master by research students. He had published more than 100 papers in a reputed journal. And then he also a very active member in IET, IEEE, IEICE in Japan, and IEM Malaysia. Okay, thank you for the time. And now the time is for you, Professor Kaharudin Dimyati. Okay, thank you.
Okay, thank you very much, Miss Lilik, and MC earlier, Mr. Akbar. Of course, I'll be very much privileged to have this session. Thank you very much, Prof. Dwi Setiawan, Dekan or Dean, Faculty of Applied Applied Technology.
Advanced Technology.
Advanced Technology. Advanced Technology and Multidicipline. And of course, to Prof. Ritna Apsari, Vice Dean, who have been in contact with me throughout since I've been appointed as adjunct professor to the faculty. And today is basically, it's very, very fortunate indeed for me to have this session. I thought perhaps I can be there, but then due to the current situations, it is not permitted though. So, but we will have this session.
Welcome, Prof. Welcome. Thank you very much.
Okay, Prof. Okay, so yeah, I will share. Basically, this is a kind of a sharing sessions. What are the research that I've been doing? As mentioned by Miss Lilik just now, basically I'm working on wireless communications as well as optical communications. The one that I wanted to share today is basically on the wireless communications, millimeter wave technology. So I believe perhaps some of you are working around the area on wireless communications. So when we talk about 5G, for example, started in 2010 onwards, where research on 5G started. So now basically research on towards 6G started. So at that point, one of the potential bands to be used is on millimeter wave. So which is 28 gigahertz. 38 gigahertz. Now people are talking about 73 gigahertz and 142 gigahertz. Yeah, and also D2D communications, because of latency requirements. We have IoTs and so on. Everything will be embedded into one integrated or heterogeneous technology. So you have a very critical or mission critical applications where you really need a very short latency as compared to those like voice communications where a bit of latency is allowed. Doesn't really affect the system very much. Okay, so perhaps I'll share my screen. Mungkin kalau share my screen. Hold on, is it desktop? Let me share my screen. Okay. I have one PowerPoint here. Open share. What is this open share preference?
Pardon, Prof?
Okay, let me. I try to share my screen. Can you allow me to share my screen? Because it seems the system does not allow.
Please, Mas Rizky. Mas Rizky. Wait, Prof, ya.
Yeah, okay.
It's work, Prof.
Hold on, let me try again. Why is security and privacy? What does that mean?
Can you
Hold on.
can you try again?
Okay, okay.
Yeah.
I'll try again, yeah. Okay, so I'll try again. Share screen. Okay, share screen.
Sudah, Prof.
Okay, so that is who can share all participants, who can start sharing all participants, yeah, because there's only host and all participants. So now I put all participants.
Yes, Prof.
Okay. So now perhaps I hope I can share. Let me. Why I can't? Oh, okay. Hold on. What happens? Share. Why they request allow Zoom to share your screen? Hold on, yeah. Hold on.
Or maybe you can share to this, Prof. I will
okay,
the
so
host will share.
Okay. All right.
Sorry,
so now
Prof,
I
for
will
this
share
problem.
my slide with.
Gimana, Mas? Kalian dengerin, Mas. Kalian dengerin.
Hold on, ya.
Dengerin ini juga.
Okay, hold on, ya. I'm not sure what happens.
Very sorry, Prof, for this problem, because this one, I don't know, it's never occurred previously like this. Very sorry.
I just already
Huh?
make you as a host, Prof.
Okay.
Can you
okay, let
try
me
again to share screen?
Let
Yes.
me try again to share. Say share the Microsoft PowerPoint. Oh, still they ask me to open system preference. What does that mean? Anybody knows? Because previously I don't have these problems. I think I will share. I will share the slides.
Yes,
So,
private to me is okay, Prof.
Okay, so
Private to me.
how
Wait, I will.
Yes.
Okay, I already message to you, Prof. Maybe you can share to me. Thank you.
Okay, so that means I share in this link, yeah?
Yes.
Okay.
So only to me, and then I will pass to the host.
Okay, so who can, is it this one? Okay, let me document. Okay. Okay, sent successfully. Can you please check?
Okay.
Okay.
Thank you, Prof.
My apology for that. Not sure what happened either. Perhaps my laptop as well.
Okay, I will also I will share. Wait, I will open your slide. I will share your your slide, yeah, Prof. I'm your operator now.
Okay. Thank you.
It's okay, Prof. I also graduated from Prof.
Oh, yeah.
Yes.
When was that?
From electrical engineering also.
Electrical. Oh, okay. So who is your
And Prof. Hazli Mokhlis, Prof.
Oh, Prof. Hazli Mukhlis.
Yes,
So
yes.
power systems.
Yes.
Okay, all right.
Very sorry, Prof, for this problem.
Okay, no
Actually, we
problem.
already done for the for previously, but I don't know why. Okay, thank you, Prof.
Okay,
The time
okay.
yours is now.
Yeah. Okay, go to the next slide, please. Okay, so a brief of intro. Next, this is the third slide. The second slide.
Okay. This one, Prof?
No. This is the first slide.
Previous.
Yeah, previous slide.
Okay.
Yeah.
Okay.
Okay. So now next slide. Okay. So this slide, yeah. So I guess as everybody can see in front of your PCs or laptops, yeah. So basically, next generations will be massive volume amount of data. Yeah, that is basically deniable. So even now with all the IoTs related devices and so on, there are massive amounts of data to be transported over our communication systems. And it is anticipated that it could possibly hit tens or even hundreds of billions of devices by the time of 6G fully deployed. Wireless communications, or especially mobiles, the cycle is around 10 years, every cycle. So it started with first generations around 1980s, then second generation 1990s, third generations 2000, and then the fourth generations 2010, the fifth generation, which is now, is the 2020. So comes 2030, I believe the cycles will repeat with the new generations, sixth generations, or people call it beyond 6G. So at that time, so basically it is anticipated that there are so many devices, even beyond the populations of the world. Yeah. So therefore, new wireless technology that can support this, is required. Since high capacity means more bandwidth, so when there are more people, more devices attached to the systems, to the communication systems, means that more bandwidth is required. More bandwidth is required, and therefore one way to go about that is through a millimeter wave. Okay, so that's why the talks of today basically focusing on millimeter wave technology. I'll focus to two basically, so which is the 73 gigahertz. Some works we have done here on simulation basis, and also 142 gigahertz. So that is millimeter wave. So by definitions, millimeter wave is around 30 gigahertz up to 100, above than 100 gigahertz. Yeah? Okay, hence it is very important to characterize this millimeter wave. Yeah. So that what are the effects? What are the effects that millimeter wave has, or millimeter waves have to different environment? Yeah. And different scenarios, because we are talking about indoor and outdoor as well. Yeah. And what are the models, okay, that perhaps mostly reflect or mostly accurate to reflect these propagations issues within this millimeter wave domain. Okay. Sorry. Next, please.
Okay, Prof.
Yeah.
Okay, this one.
Okay. All right. So as I've mentioned earlier, okay, there are massive growth of number of devices connected to the internet. Okay, and the data generated from those devices is also huge. Is also huge. Okay. Previously was commonly, processed in cloud, which is basically far from the end users. Far from the end users. Okay, that increase the latency. Increase the latency, and therefore basically a means need to be devised, so that the processing could be closer to the devices, and hence reducing the latency, which is the much needed elements or the much needed parameters, especially when we deal with, for example, machine-to-machine communications, or device-to-device communications later. So we have this, fortunately, fog computing, which was introduced by Cisco back in 2012. The idea of fog computing is distributive computing as compared to cloud computing, centralized computing. With that, basically, there are many advantages as compared to cloud computing, and we find that these advantages is suitable to millimeter wave or to 6G applications that requires very low latency. So because if you can see from the slides, okay, with fog computing we will be able to minimize the latency, minimizing the network congestions, because communications are within short distances, tackling the connectivity bottlenecks, enhancing security and privacy, and we will be able to improve network scalability as opposed to cloud computing. Of course, cloud computing, the processing massive amount of data. To a certain extent, it is necessary for some applications, but not for low latency applications. High communication latency, traffic congestions, and also connectivity bottleneck. So basically, in principle, fog computing was designed to support delay-sensitive applications as well as mobility by providing computing, networking, and storage capability at the edge of the network. So kalau you, if you see this diagram, basically at the edge of the network. Okay, next slide, please. Next slide.
Wait, okay.
Okay, so this just take one the current scenario. The current scenario. So this is basically to show you the coverage area of various frequency bands. Okay, so if you look at this, at the most inner circle will be the millimeter wave. Not to worry about this 5G. The millimeter wave. By millimeter wave, normally the coverage is lesser. Coverage area, because the signals cannot go far, but they give you a lot of bandwidth and also latency, which is suitable for certain applications. Then we have 5G mid-band or sub-6 gigahertz. So most of the implementations for 5G now is sub-6 gigahertz. So which is typically around 3.4 or 3.5 gigahertz. Okay, so and then the dynamic sharing spectrums, 5G, where this exists between 4G and 5G. So that is basically as far as the range of frequencies or range of coverage areas within the heterogeneous networks of 5G. Okay, next slide. So now what is in 6G? Those who are working along this area, or along wireless communications, there are basically papers, papers related to 6G already started appearing, and in the internet. Mostly are still at literature review and so on, paper or review papers, sorry, not literature review papers and so on. And basically what you can, this is what I can summarize, what I can summarize, not all though, of the potential features of 6G. It will be 1,000-fold or 1,000 times higher mobile data volume per geographical area, 100-fold expansions in the number of connected devices, or 100 times more, as compared to the existing technology, and 5-fold reductions in end-to-end delay, So that means it is very, very small latency is required. And basically to achieve that, so we believe that fog computing can be one of the technology that we can employ, in order to reduce the end-to-end delay. Okay, so remember, fog computing is at the edge, and it will be able to achieve this less end-to-end delay or small end-to-end delay for certain applications, and then 100 times higher data rate per user. Okay, bandwidth in millimeter wave is huge, and therefore it can carry more data, in millimeter wave system, and therefore I believe so millimeter wave fog radio access network can be one of the potential technology for 6G or beyond 5G communications. So I'll talk more on these two millimeter wave bands. One is the 73 gigahertz, the other one is 142 gigahertz. Okay, so what are the advantage of having millimeter wave? As I've said, high bandwidth, advantages, of course, high data rate, but it comes with shortcomings as well. Okay, you have advantages, you will as well have disadvantages. So now the question is how we are going to make sure that these limitations, these disadvantages, will not hinder the progress of millimeter wave technology as far as beyond 5G is concerned. Okay, so what are the limitations as listed below? Blockages. Millimeter wave wavelength is very short, C equal to F lambda. Wavelength is very short. Okay, so tend to be absorbed by blockages. Shadowing, one of the other effects. Refraction, diffractions, a signal will tend to be diffracted, and of course high path loss. Okay, rain attenuation. If there is heavy rains, the signal will be potentially be blocked by rain, for example, and also atmospheric absorptions. So we as a researcher, basically, it is to me is our duty or our responsibility to try to look into this and also try to reduce the effects of the short wavelengths for the success of beyond 5G. Oops, sorry. Yes, please next slide, please. Yeah. And therefore, it is essential to gain a better understanding of millimeter wave propagation behavior before we design the millimeter wave fog run. Of course. Okay, and then we need to characterize the wireless propagation channel by modeling the path loss. I think those who are working on propagation studies, because this on the millimeter wave part, mostly on propagation studies, works by Rapaport, for example, so he has a book which on that deals a lot with this propagation studies. Okay, so characterizations of propagation channel by modeling the path loss. So what is path loss? A measure of the propagated signal fading as a function of signal frequency and the propagation distance. Okay, next slide, please. Okay, so now what is important? So we need to optimize the channel propagation parameters, which is crucial for achieving better QoS for 6G wireless network. Okay, so the question is, what are the means that we can use or we can do to optimize the channel propagation parameters? One is to investigate the potential ability of a millimeter wave path loss model, such as floating intercepts, FI, or close-in reference point, based on real measurement. When I said real measurements, that means you have to have a channel sounding systems, okay, that can measure the signals, okay, say from the transmitter to the receiver by using the systems. Okay, then you can estimate the propagation channel model by extracting the path loss exponent value at millimeter wave frequency band. So that is one way you can try to optimize the channel propagation parameter. The other thing is we can investigate the power delay profiles at millimeter wave frequency band using an omnidirectional transmitter antenna and highly directional horn receiver antenna for co and cross polarized antenna configurations. Then we can propose a new path loss model for outdoor and indoor environment. Okay, the studies must cover both outdoor and indoor, because wireless or mobile is basically anytime, anywhere communications. It can be outdoor, it can be indoor. So both aspects has to be studied. Okay, so that is the first two is on the measurement. But for example, if you don't really have the measurement systems, perhaps we can conduct a simulation based. We can conduct simulations based on the certain trusted data. For example, okay, feasibility study of using 100 gigahertz millimeter wave bands technology in random access network to estimate the achievable data rates under different network deployment scenario. Okay, such as PPP, GPP, okay, ultra dense networks, UDN, and also square grid. Okay, next please. Okay, so now focus. So that is in general just now. So now we try to focus on 73 and 142 gigahertz millimeter wave band to estimate the achievable data rates in these networks. So this is what I wanted to show you after this. Okay, some studies on this 73 gigahertz and 142 gigahertz millimeter wave in the fog run scenario. Okay, and basically we use simulations in order to look into the parameters, the performance of the systems. Okay, next slide, please. Okay, so this is the system model basically that we used. Okay, so we have this central cloud, okay, or the earlier one. Okay, and we have the millimeter wave transmissions here. Okay, in the smaller circle here is the millimeter wave transmission. Yeah, and we have the fog nodes. Yeah, the fog nodes. Okay, so and we have the user equipment. Yeah? Okay, so by simulating this with the proposed scenarios, then we can see the performance of the systems as far as the GPP, PPP ataupun square grid and ultra dense network perform. Okay, next slide please. Okay, so this is the user models that we use. One is PPP, complete independence and randomness. So basically the users are placed at random inside the areas of concern or areas of study. Okay, so in this case, the nodes are located very close together in some cases. And in square grid, so this is square grid, which is the B part. Okay, so in square grid, it is an approximations for a Manhattan like urban environment. Square grid is good for traffic monitoring, for example. Power grid, smart metering, goods monitoring in warehouses and smart homes. So this is the potential applications of square grid systems. Is a benchmark in wireless performance, wireless network performance studies. And in ultra dense networks, okay, so in ultra dense networks, the number of fork nodes, lambda fn, must be greater than lambda u, the number of users. So that means the fork nodes is more than the users. You have seen in the previous slide what are the fork nodes. And it is essentials technology for 5G and beyond. So basically, when we say the 5G and beyond, we are talking about ultra dense environment. Okay, because that is the aim or the purpose of this technology, to support ultra dense environment. Okay, and it is indeed a high data rate. Okay, next slide please. Okay, so this is some examples. So this is quite a normal equations. Quite normal equation. Path loss is equal to free space path loss plus 10n, where n is the path loss exponent, log 10, the distance between the transmitter and the receiver, and divided by 1 meter, and plus some standard deviation. Okay, so and the free space path loss is given by that equation. Okay, and chi sigma is the shadowing, is the shadow in dB, in dB, which is a Gaussian random variable. And of course, when we are talking about millimeter wave, so effect of oxygen attenuation has to be taken into considerations as well. Okay, some of the parameters important. Next slide, please. Okay, antenna pattern as well. Okay, so these are the gain in dB for the antenna pattern. Okay, so it is a standard equations. Next slide, please. Okay, and capacity calculations. Again, it is a Shannon formula. Something which is very common formula. Bandwidth times log to 1 plus SNR. Okay, so this is the signal, this is the noise, and this is the interference. So the signal to noise interference ratio in this case. So these are the respective equations for the signals, for the interferences, for the noise, and this is the noise in the BM. Okay, and this gives you the capacity, the capacity of the systems by using a Shannon formula, a very well-known formula for capacity calculations. Okay, next slide, please. Okay, so and then we try to look at what are the parameters that is important. Fork node height, fork node is basically the small base stations. 6 meter user height, basically 1.5 meters. So us basically this one, and we try to simulate the the environment. Okay, just now with GPP. Tadi GPP, then we have apa tadi, square grid, and also ultra dense networks tadi, okay, and we try to simulate and see what is the performance like by using the 73.3 or 142 gigahertz based on line of sight scenario and non-line of sight scenario. LOS is line of sight, yeah, and N loss is the non-line of sight. Okay, so this is the path loss exponent. You can expect N loss path loss exponent should be higher, yeah, because losses in non-line of sight will be higher because there are a lot of blockages between the transmitter and the receiver, and that is the one taken into account for the path loss exponent for N loss, to be able to reflect accurately when we do the calculations for the propagation studies. Okay, indoor, outdoor. Okay, so outdoor, this is the examples of 73 gigahertz. Yeah, this is for outdoor. This is for 142 gigahertz indoor. Outdoor. Sorry, outdoor loss and N loss. Okay, so these are some of the parameters important. If you want to do a actual measurement, say you have the equations in the university, for example, the equipments. Okay, so you have to do it. You have to do your studies out. By using the equipments, the channel sounding systems. Okay, to see or to measure, how the signals propagate from the transmitter to the receiver. Okay, next slide, please. Okay, so this is the typical. I just wanted to share with you the typical methodology. The typical methodology that we use normally in measuring the propagation studies, or in doing the propagation studies for these 2 millimeter wave systems, or 2 millimeter wave signals. And the same methodology you can apply as well to other propagation studies, because the methodology are quite similar. The difference is the bands used, and also perhaps the environment, but still in Malaysia or Indonesia, still tropical countries, it is still tropical environment. So as usual, the research will start by studying and analyzing existing literatures, setting up the testing environment. Yeah, of course, if it is at very high frequencies, like above 100 gigahertz, the equipments are quite expensive. Okay, collect the raw data for the above 100 gigahertz to outdoor and indoor, and compare with, for example, 38 gigahertz or 73 gigahertz. It is up to you. Say if you are working on 28, perhaps you compare with sub-6. Yeah, just compare to see that what you are doing is on the right track. Yeah? Okay, then after that, after you collect your data, you analyze the raw data using I use MATLAB. We use MATLAB here to analyze and extract the channel response in terms of a large scale path loss with distance and path loss exponent, and we can also define the propagation behavior, determine the object penetration, what are the effects, or how does reflection, scattering, diffraction, and absorption affect the signals with respect to different scenarios and environment. Say for this case just now, with respect to PPP, with respect to GPP, with respect to square grid, with respect to UDN, for example. And then again, we analyze the raw data. Okay, from there, we can, after we are happy, for example, say, yes, this is the work seems to be right. Yeah, the result seems to be right. Or after comparing with the existing, okay, then you can propose a new path loss model for the existing study in millimeter wave. Okay, example of popular path loss or existing path loss model like the COS 231, for example. Those who are working in the area, I believe you know COS 231, Hatta model, Okumura model, and so on. Perhaps later, if you really do on this, it can be Airlangga's model, for example, or UM's model. That can be. If we do it successfully and accepted universally or accepted worldwide. Okay, some small scale parameters also need to be taken into account, like root mean square delay spread, root mean square delay spread, mean excess delay, dispersion factors, maximum excess delay parameters, and so on. So these are so these slides basically shows quite a standard methodology in propagation studies. Okay, next. Next. Okay, so now we look at some results, okay, for the various environment just now. So now we look at 73 gigahertz millimeter wave fog current. Okay, and the simulations environment is PPP. Okay, so in this case, we fix the number of fog nodes to 100 fog nodes per kilometer squared. And we want to study the impact of user density. So this is user density. So the impact of user density on the achievable channel capacity. So this is the channel capacity. As we can see the pattern here, as the number of user density increases or the number of users per kilometer squared increases, the channel capacity decreases. Okay. And then if we look deeper, loss versus N loss, for example. So we have loss indoor, N loss indoor, loss outdoor, N loss outdoor. So if you look at this, the indoor channel capacity shows better performance than outdoor. Outdoor. Reason being, the indoor environment receives signals are supported by reflections from wall. Okay. Reflections, so because there are many reflections, and in this case, this reflection reach the receiver at the same phase. Okay, same phase. If they reach at the same phase, then the signals will add ons and making it a stronger signals. So, but of course, if it is out of phase, then you have problems. Signal can diminish. Okay, so basically, yes. Okay. Yeah, basically, it's when you deploy the systems, you have to take this into account. Okay, then we have, if you look at the N loss, N loss indoor, N loss outdoor. Okay, so in this case, we can see that N loss indoor. So this is N loss indoor, the third one, and N loss outdoor. So N loss indoor performs better than N loss outdoor. So this is because the channel capacity of N loss indoor is supported by reflections of signals, whereas the outdoor signal is scattered. Because it is outdoor. So there is no reflections generally, signals are scattered. Okay, so and then the channel capacity is close to 0 in this case. Okay, so and then so this is the PPP deployment scenario for fog nodes is equal to 100 and channel capacity versus user density. Then the diagrams below is channel capacity versus fog nodes, or for fog nodes density. Okay, we maintain the number of users, okay, and increasing the number of fog nodes. So if you go back to the slides earlier, the fog nodes is basically the smaller base stations there. Yeah. Okay, so we can expect basically from this that as the number of fog nodes increase, the capacity will be increased, because the fog node is the one who gives you the throughput or capacity. Okay, next slide, please.
This one, bro.
Next one. Next one. Yeah, next one. Okay. Any next one, 142. Okay. Okay, so if you look at this, ini bukan yang tadi?
Bukan, bro.
Bukan, Okay, all right. Okay, it's if you look at this, the patterns is similar. The patterns is similar. The difference is on the channel capacity, because it works at 142 gigahertz. Okay, next slide. Okay, so mana yang square grid tadi? Bukan. Patah balik. This is UDN square grid dulu, square grid. I think a slide before.
Prof, I think my laptop also like.
Okay.
Sorry. Okay, this one, square grid.
Yeah, okay. Yes,
okay,
correct.
thank you.
Okay, so now is the square grid scenario. Okay, square grid scenario. If you can look, the patterns are the same. Yeah, because the number of users are almost the same. And then we can expect, okay, the patterns are quite similar. The difference is on the channel capacity or the output. Okay, for the UDN, the next slide. Okay. Now, for UDN, as I've mentioned earlier, the characteristics of UDN is lambda F must be greater than lambda U. Yeah. Okay, and typically lambda F is greater than 1000. 1000, or the fog nodes, the number of fog nodes ataupun lambda F is greater than 1000. The one that we simulated here is 1000. Okay, to show that it works. Okay, and also the number of users. If you still remember back a few slides back, typically it is around 600. Okay, but here it is 200. Okay, no problems. Just as a use case. So as we can see here for UDN deployment, okay. So basically, again, okay, as the user density increase, because we maintain fog nodes, then the capacity will be decreasing, and as the number of fog nodes increasing, okay, and the or we maintain the number of users as 200, even though the minimum is 600, as I've mentioned earlier. Okay, but we simulated using this, so we'll just wanted to show the patterns, the patterns. Okay, so which is should be the patterns. Okay, so we can see that as the number of fog node increases, the channel capacity increases, which means better ability to serve the users at a given geographical area. Okay, next. Okay, So what we can observe from the previous exercise, basically, or from the previous slides, massive accumulations of interference component can severely impact the performance when the density of Fn is low. Okay, just now we see some Fn low and some Fn high. Then increasing the density of Fn is significantly improve the performance. Okay, so that's why it is very important. Then Fn deployment strategy with higher degree of regularity performs better. UDN is less vulnerable to interferences. Okay, so which is good here. Okay, so this is basically the first part. So this is the first part on the millimeter wave technology. So to sum up, basically, so millimeter wave technology to me will be the next technology important in mobile communication. So I believe works on millimeter wave is very timely, very timely. Okay, and there are many papers. There are many papers currently looking into this, be it a review paper or some technical papers. For those who are interested, perhaps can start looking into higher frequencies, because the promise of higher bandwidth and the bandwidth that is much needed, the bandwidth that is much needed in the next generations of wireless communications. Okay, so now we go to the next part. Okay, yeah, D2D communications. D2D is device to device. So that means your systems connects, or your device connects directly to the other device without going through the base stations. Okay, so in a case, it's a kind of ad hoc network. So device to device communications is one of the essential components of the future 5G or beyond 5G, or sometimes it's referred to 6G mobile network. It supports high speed peer-to-peer data transmissions. Unlike traditional cellular communications, device-to-device technology work partially with or without the existence of the base stations infrastructure. You can form D2D networks without the base station infrastructure, or you can as well form with the assistance of base station infrastructure. Okay, due to the flexibility of network deployment, spectrum utilization, and extend network coverage, so device to device as well can be used to extend the network coverage. Perhaps, for example, I give you one example for this extending network coverage. Say the base station ends at one point. The base station ends at one point. Okay, the coverage of the base stations. Beyond this, there will be no coverage. So you can form D2D beyond this with one device connected to the base stations, become the kind of base station, ad hoc base station for the device to device networks. This is especially important during disaster events, ataupun I put there calamitous events, okay, such as an earthquake, flood, tsunami, etc., where the established cellular communication infrastructures may become dysfunctional in the area or in the disaster area. So in such situations, the devices within that disaster area can form D2D communications, okay, and connect again the device nearest, or the devices that is able to connect to the base stations become the base stations for that particular D2D, that particular small networks. Okay, so these functionalities, attributes, and features of the D2D communication has offered opportunities for extensive research explorations. Again, as I mentioned, during disaster areas, or even if during non-disaster areas, you can form your own D2D communications for the purpose of, say, mission critical applications. Okay, again, goes back to earlier, some of the earlier said when we talk about mission critical applications where latency can be of important parameters. Yeah. Okay, in the developments of future B5G wireless network community. Okay, next slide, please. Okay, so I wanted to focus more on this resource management elements in D2D. Yeah? Okay, there are many elements that we can consider, but for today, I'll focus on this resource management elements. So what are in resource management D2D? What is important criteria for having good management of resources, yeah, in D2D communications? One is through power allocations. Okay, power allocations can be FDD based PA power allocations. So of course, this is a summary of it. You can do extensive literature for this. Yeah? OFDMA based, yeah, or NOMA, yeah, non-orthogonal multiple access based power allocation. These are some of the summary, okay, on resource management in D2D as far as power allocation is concerned. Then spectrum allocations, yeah? Allocating spectrum. You have katalah that millimeter wave band. The band is huge. Okay, so now how do you manage this huge band to uplink scenario and downlink scenario, for example? And then interference management. We have to manage interference. Yeah, there are many interferences. In the system. So perhaps we can look that into what are the sum rate, what are the capacity and network utility, and then mode selections. It must be energy efficient based mode selections. It can be spectrum efficient based mode selections, or it can be different, distance based mode selection. And all of this basically, there are a lot of literatures associated with. I just summarize some points important as far as power allocation is concerned, spectrum allocation is concerned, interference management is concerned, and mode selection is concerned, as far as the managing resources in D2D communications. Next slide, please. Okay, so these are the issues. I believe some issues that are is good for future research. Yeah? Okay, yeah, next slide, please. Okay, power allocation. Okay, so perhaps power control, yeah, is an important aspect to achieve a reliable and efficient communications. Yeah, very important. So with the limited resources and the increasing burden on the base stations, user experience QoS. Yeah, user will experience QoS degradations. Okay. So basically, so these are some of the issues that we need to tackle under power allocation. So in B5G D2D communications, D2D users are in close proximity. Yeah, they are close to each other and communicate easily, and hence consume significantly less transmission power. So which is good. Yeah. If you can, for example, compartmentalize, yeah, compartmentalize the big systems into a smaller systems, yeah, which is here we can say it is reflected in D2D. So it will they will be in close proximity or closer to each other, and therefore consume less power, transmission power, than the normal cellular users. Yeah. To use resources more effectively, it is important to control the power user equipment. Yeah? Hence, D2D users should reduce the transmit power to meet the SI and R. Yeah? If you remember earlier, capacity, yeah, or the the Shannon's equations earlier. channels capacity equation, S, I, and R play a role there. Okay, next slide, please. Okay, so this is what I thought perhaps some of you who are in the area may agree or may not agree. Yeah, future research need to focus on efficient power allocations, which is essential for maximizing energy and spectrum efficiency. Yeah? Okay, as much as possible, we want our D2D systems has a long life. Okay, has a long life, so that it can be able to communicate or serve well the users. Yeah? Among the solutions proposed to overcome power allocation issues are that one, say energy harvesting concept, RF energy harvesting, interference signal energy harvesting, and adjacent source energy harvesting. So these are the energy harvesting strategy or energy harvesting techniques that we can use while the signal, or we can use to collect energy while the signal is on transit. Focus also needed on optimal power transmissions. Okay, so we need to look into this as well. Optimal power transmission. Power allocations may be classified in static or dynamic. Yeah, in static, the transmission power is constant and unaffected by the situations changing, while in dynamic, the transmission power could be changed based on how close the devices are to each other. Yeah? Okay, so there are some of the issues that we can try to solve within power allocations resource for resource management. Next slide, please. Now spectrum allocation. Spectrum allocations, I guess, is quite easy enough, yeah, because you have huge spectrums in millimeter wave, for example. Then we can how we want to allocate the spectrums. Yeah? So in B5G, D2D is important for increasing cellular network spectrum used. Yeah? Effective distribution of spectrum resources inside the cellular system is a significant challenge. Yeah? After the nearby device discovery and mode selections, the spectrum allocations of resources must be optimized to achieve the goal of D2D communications. Moreover, when allocating resources, interference management and power control must also be taken into account. Yeah? Okay, two kinds of spectrum access, underlay and overlay. So what is the difference? Underlay communication scenario, D2D users and cellular users share the same resources. Yeah? Overlay, portions of the resources is dedicated to D2D communication. So that are the difference between underlay and overlay communications. Yeah? In spectrum allocations. Next slide, please. Okay, so both underlay and overlay scenario, the development of efficient and intelligent resource allocation strategies is crucial. So in addition, most of the research, this is based on our literature search, most of the research that has been done consider centralized spectrum allocations, which is done by macro base stations. So this will degrade, yeah, the QoS. So that means you can have decentralized or distributed spectrum allocations in this case. Yeah? Should be fully distributed and intelligent to overcome, yeah, the burden on the base stations, yeah? Because we want to reduce the burden on the computing at the base stations. Yeah? Okay, next slide, please. Okay, so interference management. Yeah, so this is the main problems in heterogeneous networks. Yeah, interference. Yeah? Even in 2G or 3G last times as well, we discussed a lot on interference. Yeah? Interference, when the signals are interfered, basically the capacity, yeah, is limited. Yeah? So now how do we try to address this? Yeah? Okay, so D2D pairs may operate in either in-band, okay, license, yeah, license bandwidth, licensed or outband unlicensed bandwidth. Yeah, example of unlicensed is 2.4 gigahertz bandwidth, yeah, or 5 gigahertz bandwidth. Yeah, whereas the rest of the bandwidth, the one that used by telcos, used by 2G, 3G are all licensed bandwidth. Okay, so D2D may operate in either licensed or unlicensed band, in which the transmitted data of one device can influenced by the surrounding devices. Thus, cellular devices are harmed by the disruptive interference caused by the other communication devices, which led to degradations, yeah, in the network performance. Yeah. So what are the techniques that we can use? Yeah. We need to have an effective spectrum sharing and power control strategies to enhance the network performance and reduce interference. Okay, so if we go back to 2G, for example, there are techniques to reduce the interference, such as, you know, reducing the power transmit so that it does not really interfere to the next cell, yeah, or basically split the cell into, say, 2 to 3 smaller cells, yeah? Yeah? And so on. Yeah? So the similar strategies we need to employ here to reduce the interference or to manage the interference within within D2D environment. Yeah. Okay. Next slide, please. Okay. In B5G, the integrations of D2D technology and heterogeneous cellular network leads to sophisticated interference management. Therefore, interference mitigations issue of D2D with HeadNet is an open topic for future research. Yeah. Furthermore, by using effective and intelligent solutions for interference reduction, the attainable data rate as well as the quality of service for end users may be significantly enhanced. Yeah? So, in essence, basically, we want to reduce the interference in this heterogeneous network, okay? Okay, of beyond 5G or even now 5G. Okay, so next. Okay, and I think this is the last slide, if I'm not mistaken. Mode selection. Yeah, mode selection is defined as the process of choosing between cellular or D2D mode. Yeah. Okay, you have cellular mode, connecting yourself to the base stations, or the D2D mode, where you form your own small networks in this mode. So after selecting the appropriate mode, the device should decide whether to reuse the direct link or cellular link. Yeah? Okay, direct link means within the D2D modes, and cellular links connecting yourself with the cellular networks. There are 2 modes of selections to perform: bit static before the establishment of D2D connections, or dynamic according to the time slot. Yeah? Many factors affect mode selections: channel state information, or CSI, time scale of mode selection. So these are some of the parameters. Yeah? Some of the parameters or some of the factors that we use in mode selections. Yeah? The distance between D2D transmitter and receiver, SI and R, path loss, and also battery life. Yeah? So mode selections overhead is one major challenge that we should address. Yeah? So the mode selections procedure might result in a huge amount of overhead. Yeah? So we need to reduce basically this overhead when we use mode selections as part of managing the resources within D2D communications. Yeah. So next slide, please. I think this is the next slide will be, yeah. Okay, so basically that D2D communications, I focus on resource management within D2D communications. There are many more aspects, many more parameters that we need to consider within D2D communications that is important to improve or to make best from the concept of D2D communications. Yeah? So with that, I thank you very much for listening. So to recap, basically a kind of two topics. Yeah, one is on millimeter wave technology, and the other one is D2D communication. Focusing just now for D2D communication on resource management. And it is anticipated to be part of beyond 5G mobile communication systems. Yeah? So with that, thank you very much, and back to Ms. Lilik.
Okay, thank you very much, Prof, for the very interesting topic and discussion for today. Okay, for now, I open for the Q&A session, Prof.
Yeah.
Maybe three participants first, maybe can raise hand, or maybe can write down in the chat room.
Yep.
Okay, three participants first. I stop share, Prof. Thank you.
Stop share, boleh stop share.
Okay, is there any question? Okay, from first we have a two which already raised hand. Maybe this from siapa nih? Muhammad Hafiz. Yes, Muhammad Hafiz. Okay, time is okay.
Okay. Okay. Good afternoon, sir. My name is Muhammad Hafiz.
Yeah, Muhammad Hafiz, proceed.
I'm addressing the most common concerns regarding 5G. I'm sure you've heard this a lot when you talk about 5G, which is the health concerns that 5G waves could cause cancers and stuff. What is your take on this? And because also my second question is as described before, that 5G has a lot of interference issues regarding blockages and stuff, and we need to have a lot of nodes to comprehend those. And because there will be a lot of nodes, which would be a logistical nightmare. What is your estimation on this 5G network to be widespread use around the world, to be as normal as 4G now? That is okay. That's my question. Thank you.
Thank you, Hafiz, just now.
Yes.
Okay. The first questions, on health issues. Okay, so any basically technology. I think not only in 5G, even previously in 4G as well, health issues has been of concern. But all basically devices comes with, they call it the specific absorption rate or SA, which is if you are able to meet the requirement of that SA, which is the specific absorption rate for each devices or each components within the systems, health issues should not be a problem. So I didn't say totally zero, but within a limit, within an acceptable limit. So perhaps that is my first answers to your first question, or my answers to your first questions. Okay, and then the second question is, now you are talking about so many nodes, right? So many nodes. I have to recap correctly your questions. I remember so many nodes because I forgot to jot down just now. So many nodes in the systems, because you have the cellular, the non-cellular as well. I think that is what you mean, right, Hafiz?
Recap of the question is
right. Yes, please.
the estimation of time that this technology would be practically available as 4G right now, because it's a logistical nightmare with millions of nodes. I can imagine now.
Okay, the
Yes,
practicality of I think that will be depending on
Video call.
what is that? Okay, that is depending on the push of the telcos in in respective countries. As far as the push to I think that is my answer to that.
Thank you.
Okay, all right. Yeah, just now they said video call in progress. What is that? Next. Just now there is two person just now.
Okay, Prof. For next, Mas Akbar previously already present. Hello. The next question.
Hello, Bu Lilik.
Okay.
We have the same question with Hafiz talk about the health issue, because because we know in quantum physics talk about the wind theory. The smaller wave, so the biggest energy release from the wave, so it can be it's concern about human health.
Yeah,
we have the same topic to, in the question.
Okay. So I hope my answers just now satisfy you. Okay. Other question?
Hello, Mas Akbar.
Yeah.
Okay.
Okay, it's already satisfied, Prof. Okay, maybe for the next question, is there any participant directly?
There's the
Okay, Prof.
DS Samson on the chat.
Okay.
Yeah, I saw there is one on in the chat.
One from the chat. How
Yeah.
is your opinion about smart grid? Do you think the telecommunication engineering could contribute in those area? Thanks you, Prof. Thank you.
I think this when you said smart grid, it is related to power systems, right? This one, am I correct? The smart grid.
Yes.
Correct. Yeah. Okay. So now, definitely it is telecommunication can contribute, because data from smart grid. How do you transmit all the data that you obtain from smart grid? Yeah. So one means is to telecommunications, through telecommunications. Yeah. And I believe the answer in this case for me is yes. Telecommunications will contribute on that one, especially in the heterogeneous network. Perhaps within the smart grid network, it is not directly linked to telecommunications, to the base stations, but the network within that smart grid, and then communicated through the telecommunications network. I hope that answers the question.
Okay. Thank you, Prof. Maybe for the next question from lecturer also can, maybe. Okay, from Bapak Yusrizal Afif.
Okay,
Silakan Pak
thank
Yusrizal.
you. Thank you so much. Okay, I want to ask about the technology itself. Based on your research, Mr. Kaharudin.
Yeah, okay.
Will the old device be able to adjust with the new technology, or we need a new gen tech device itself? So we can use the new gen technology. This is 5G, right?
Yes.
We can use 5G telecommunication in optimized 100%, because for the old device, for example, like iPhone 5 or iPhone 6, if I'm not wrong, 4G itself is cannot. Yes.
It is a bit unfortunate in that case. Your devices must be compatible with the technology.
Okay, that means we need a new gen device to 100% optimize.
Yeah.
Thank you.
You use result lecturer, yeah?
Yes, sir.
Ah, okay. So your research area, perhaps you're just asking use results in
In
your
high voltage and installation, sir.
again?
High voltage.
Oh, high
High
voltage.
voltage and then
Same as perhaps the chairperson lah ni.
yeah.
Yeah, all right. Okay, good.
Thank you so much.
Waalaikumsalam.
Okay, thank you, Pak Yusrizal. Maybe from the other. Okay, this is we have another question from the chat room, Prof. Is there any side effect of the 6G development for the environment? Oh, this one for 6G, Prof. Thank you.
Okay, it's quite a broad question kat sini. To me, it's very broad questions, yeah. But I think in any, not only in 6G but before as well. There is some, okay, but then to the acceptable limits, like earlier question. I think this is quite similar to when you asked about apa tu tadi, Hafiz, asking about health concern and so on. Yeah? So as long as meeting the specification, for example, yang health concern tadi sah, then we are okay with that, or we are safe basically. So just take that as an example. I hope that answers the question, because the question is too big basically. Yeah, just I answer with respect to one example just now, health concern. So it is still environment as well. Yeah, I hope that answers.
Okay, thank you, Prof. Hopefully this answer the question. Maybe from the other audience here. We have still have 2 minutes from before we closing for this event. Is there any question more? Okay, Prof, maybe I have one question if you allow to me to.
No problem.
Thank you, Prof.
Okay,
Okay, actually I interesting with the smart grid technology. And what do you think, how deep this your area will impact to our smart grid technology? If this one we is it smart grid should have this technology, or without this technology we can do for the smart grid? Okay, thank you, Prof.
Okay, smart grid, as I understand it, yeah, because I'm not really in smart grid area. As I understand it, okay, smart grid basically the idea of smart grid, we want to transfer the data that we achieve at various points within the power networks to be analyzed elsewhere. Am I correct?
Yes, Prof.
Yeah, okay. So basically, how do we transmit? Yeah. So basically through networks, and typically it can be either wired or wireless. Used to be last time they call it power communications. Young communications by using that one, but that one does not really pick up. Now the best means is through wireless sensor networks. Okay, so wireless sensor networks is basically, because 5G or 6G, it is an heterogeneous network. Yeah? Even the D2D can be networks on their own before connecting to the telco. So basically it's similar to this in smart grid. I believe it will be along that line.
Okay, thank you very much, Prof, for the talk. Very interesting talk. So maybe another question. Maybe I think this one is end of the Q&A session, Prof, because the time is
okay.
Time to closing. Okay, Thank you very much, Prof. Kahar. Maybe we can see on offline, hopefully. Inshallah, Prof. Okay. Okay. Thank you very much for once again from me as a moderator, and very sorry for the trouble previously, Prof.
My
Because
apologies
this one
as
is
well.
online. Okay, thank you. So the time is I back for MC. Mas Akbar, the time is for now.
Thank you,
Thank
Prof.
you, Mrs. Lilik.
Thank you, Prof. Retna, for inviting me.
All right.
I hope it is beneficial.
Okay, happy.
Sure,
Maybe,
Prof.
yes, sure. We can continue maybe about the research collaboration, maybe for teaching collaboration.
Yeah, we
Because
can have another meeting for that, Prof. No problem.
Okay, because we meet with the dean, I think is all of the no problem. Okay. Thank you.
Okay, thanks. Thank you for the speaker who have delivered the topic in today. Hopefully, today's event can give positive impacts for all participants. Finally, I am Akbar Syahbani, as the representation of the committee, who thanks to all participants who have been willing to take part in today's event. And we are apologize for all the inconvenience during the webinar. Thank you. Good afternoon and see you in the next event.
Okay, thank you very much.
Okay, thank you
Prof,
all.
salam from Pak Dekan. Pak Dekan, is there some meeting?
Oh, okay. Pak Dekan ada meeting lain.
Ya, ya.
Salam saya kepada dia juga, Prof. Retna.
Ya.
Okay.
Thank you.
Okay.
Kasih
Okay,
Bu Lilik, nggih, Mas Akbar,
Matur nuwun,
nggih.
Prof. Retna, Pak
Yanti,
Dekan, Prof.
semuanya,
Kahar.
Pak Agus, Pak Prisma, nggih. Matur nuwun, nggih.
Matur nuwun.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.